All right, guys, today we are talking about making predictions with probabilities. So just to review our checklist for the week, you have simple probability, making predictions lessons, as well as the last 3 lessons of the 15, which are areas of triangles, circumference, and area of circles. Please, please, please do not forget that all your lessons are due by June 30th successfully in order to make it into pre-AP math next year. The first thing that we want to talk about is some vocabulary. So a quick review of some words that we talked about in the previous lesson. Probability is the likelihood of something happening or the chance that something happens. Experimental probability is the probability of an event determined by carrying out a simulation or an event or an experiment. And remember how we discussed in the previous lesson that experimental probability is what does happen. So this is when you actually do the experiment, and what does happen is your experimental probability. Theoretical probability is the expected probability of an event, or what should happen. When we get to sample and population, let's say I want to find what the favorite color of Harvey is. Well, I don't have the time to go ask every single one of the 840 kids, which would actually represent the entire population of Harvey Junior High. So instead, I would ask just a sample. So a sample is a smaller portion of people that we use to poll to represent the larger population. So I can draw a Venn diagram to show that. So if this is my population of Harvey Junior High, I would just ask a smaller portion of it, or my sample, to get enough data to represent the whole. And lastly, a proportion is a statement of equality between 2 or more ratios. So remember, we have 1/2 would be proportional to, say, 2/4, which would also be proportional to 3/6, and the list goes on and on. Now, please remember that proportions are multiplicative in nature, meaning we multiply or divide to find these equivalent ratios. So our first problem is if I'm rolling a 6-sided number cube, or dice, the probability that I roll a 3 is 1 out of 6. If I roll that same number cube 30 total times, how many 3s can I expect to roll? So I'm thinking about it in the sense of rolling a 3 over the total number of times. Well, they told me that the probability, theoretical probability of rolling a 3 was 1 out of 6. So I want to know how many times could I expect to roll that 3 out of a total of 30 times. Since 30 represents my total, it will go in the denominator of the second ratio. And I see automatically that I have a multiplicative way to get from 6 to 1 by dividing by 6. So I would do 30 divided by 6 to get 5. So I could expect to roll 5 3s out of a 30 total rolls. So 5 times would be my answer. Our next problem. About 10% of the population is left-handed. Use that statistic to answer the questions below. In a classroom of 20 people, so my total classroom is 20 people, how many would I expect to be left-handed? Well, if only 10% is left-handed, that is actually 10 out of 100, since percents are always based out of 100. Well, 10% out of 20 people, so 20 represents the whole, so it will be in my denominator of my second fraction. And again, I'm seeing that I can divide. I can divide by 10 right here. So if I divide by 10 on the first ratio, I would divide by 10 on the second to get 2. So I would expect 2 people to be left-handed. Well, now I can take that same thought process now to my school. So in a school with 1,000 people, how many people would I expect to be left-handed? So again, my percentage, my 10% out of 100 did not change. But now my second ratio in this proportion will, because now my total is 1,000 instead of 20. And I'm still seeing a multiplicative way, so I can divide by 10 to both ratios. which means 1,000 divided by 10 gives me 100. So I would expect 100 people to be left-handed. Well, we want to know, are these numbers exactly how many people will be left-handed or just a prediction? Well, it's obviously just a prediction because we don't know until we go and ask all of those people. I have a batting average of 25 hundredths. Really quick, 25 hundredths. They told me was 25%. I know that's also 1 out of 4. This means that the probability of me getting a hit is 25%. I have 520 attempts this season. How many hits can I expect to get? So if I write my word ratio, that's hits out of my total. And I know that the probability that I get a hit is 1 out of the total 4. But they told me I had a total of 520 attempts this season. So 520 will go in my denominator. And again, I'm seeing I have a multiplicative way to get from 4 to 1. I can divide by 4. So when I divide 520 by 4, I'm going to come over here and show my work. 4 fits into 5 one time, so I will take away the 4, which leaves me 1, and that 2 comes down. 4 goes into 12 3 times, so I take away that 12, which brings down the 0, and 4 will go into 0 0 times. So out of 520 attempts, I should expect to get a hit 130 times. So 130 hits out of 520. Juan is watching cars go by on the road. He counts 10 out of 100 cars that are silver. This means that his experimental probability, or what did happen, of seeing a silver car is 1 out of 10 or 10%. This table over here represents the distribution of car colors in North America. So this is what he should have seen. And then what he did see was 10%. We want to know which statement is true. Well, the information in the table must be wrong because it does not match the experimental probability. We know that experimental probability and theoretical probability are not always equal because what does happen is not always what should happen. So that is incorrect. If he observed more cars over time, his experimental probability would get closer to the percentage given in the table. I'm thinking this sounds right because the more cars he observes, the more it will get closer to what should have happened. Now let's look at the next two. He must have miscounted because it does not match the information given in the table. That's not right. He did not miscount. And then if he observed more cars over time, his experimental probability would get further away. Well, that doesn't sound right either because the more he observes, the more his experimental probability should match the theoretical. So we are going to say if he observed more cars over time, his experimental probability would get closer to the percentage given. And that concludes our lesson for making predictions using proportions. If you have any questions about this lesson, please come to office hours Monday through Thursday, 10:30 to 11:30.